Hi again. I'm Lennart Poettering. I talked yesterday about systemd, and today I'm going to speak specifically about containers in systemd and how they relate. I know that I speak very, very fast, and I'm sorry for that. I try to speak slow, but usually during my talks I tend to forget that. So if I'm going too fast again in the middle of the talk, please just tell me, and I'll try to slow down again. Yeah, so containers, of course, everybody knows what containers are, right? Like it's a hot, awesome, big thing of today. There are many implementations currently. There's Docker, which is probably the most famous one. There's Rocket. Or actually, it's not called Rocket anymore. It's now called like just lowercase RKT. There's LXC. There's libvirt LXC. There's OpenVZ. In systemd, we have another one, which is called systemd-nspawn, in combination with something called systemd-machined, in combination with something called systemd-importd. Now, if you compare these implementations, of course, the first question you have to ask is, why does systemd even have a little container manager? Like, I mean, there are already so many implementations around. Why do we need another one in systemd itself? And that's absolutely a valid question, right? But to give an explanation, like why that happened, why we added that, we believe philosophically that containers are really should be part of the OS concept itself, right? They should not be something that you add on top, but they should be something that the operating system knows about, right, from on all levels of the stack, right? The inspiration here, the big one, is Solaris Zones. Solaris Zones is a feature of the Solaris operating system. It's like 15 years old now or something. Zones is just a different name for container. And they had that 15 years ago. They had this really, really deep integration of containers into the operating system. Solaris is kind of dead now, but I still believe it's a great inspiration for designing an operating system. And so we thought, okay, if Solaris does that, given that containers are really something where, how I personally believe that an operating system should run these days, maybe we should just do it in the lowest level of the operating system and introduce like the container concept everywhere in all the tools that we have in the lower level parts of the operating system. The big concept that we try to follow here is actually different from many of the other container solutions, because it's actually, we care that the OS running inside the container is as similar as possible to the OS running outside of the container, right? So this is different, for example, like what we try to solve here with the tools that we have in systemd, like systemd-nspawn. What we try to solve there is really something where we basically run more or less complete operating systems inside of the containers, while Docker usually focuses on microservices where you basically run one service or so, or maybe two inside of each Docker container, but not more. So yeah, it's a different focus, right? With our tool sets, we just think that, well, if you develop your application for Linux, it shouldn't really matter if the application is running inside of a container or on the host, right? If you look at Docker, of course, it's slightly different, because inside of the containers you get you lose a lot of the functionality that the host otherwise offers, right? You cannot talk to local services and things like that, just like that. So the way, I usually tend to call this integrated isolation, because on one hand it is isolation, right? The containers are isolated from the host, the containers are isolated from each other, and they appear as if they were completely separate nodes in the network. On the other side, they're much more integrated than, for example, a VM would be, or an actual physical machine would be. In which way integrated we'll see later in the talk, but it's basically about the fact that if you run multiple containers on the same host, you can actually reach a level of integration, like you can, because you have access to the file system, because you have access to the processes from the host and all these things. Yeah, so you can achieve a level of integration that's otherwise not possible, and make the containers and the host relatively well integrated by also isolating them out. Yeah, I already mentioned that. Features that the container system provides should also be available to the host system, right? Like this is or this actually specifically goes in the direction, like if you use something like Docker, right? You have all these things where you can update Docker images and download Docker images. We personally believe that actually such functionality should not actually be specific to containers. It should be applied to the host as well, right? So if you download an image to run it inside of a container, it should be pretty much the same way as you would download an image and run it in a VM or run it on the host, right? The distinction, like the distinction between how you run it should not be have an effect on how you download it, right? So with the stuff that we did in systemd, we tried to focus on a certain set of design, like there were certain things that were important for us in the design. The first one is it should be minimal, right? Like because I mean, there are implementations of container managers like LXC, which are relatively complex and very comprehensive. They support many options for the same things. Like, for example, they have a couple of storage backends, and Docker has that too. For us, we thought, okay, we'll keep things minimal, right? We will write a minimal container manager that will run a good selection of containers, but it will not provide more than one implementation for each feature, right? It will only do one storage backend, it will do one whatever, and then it wouldn't even be called a backend, right? Like, because it's just built in. What's also very important to us is we really want to focus on getting the low-level parts right. So, I mean, we are from the systemd project, so that was kind of always our thing, that we actually try to fix things properly. The other side of the medal is we will not be able to deliver a lot of the features that the other container managers provide right now, simply because we still think we need to do our homework first and fix them properly. Yeah, we also care about that we don't want hacks, right? We want a clean, integrated implementation for everything that we do there. Like specifically, this means, for example, like many of the container managers support something like device virtualization, where you can pass a device node from the host into the container. And we don't do that in nspawn. We will not claim that this is officially supported, simply because the Linux kernel doesn't do device virtualization, right? And it's not just about handing a device node through to a container. It's also about enumeration, right? Like what you see in sys needs to reflect what you see in dev. And since /sys is not virtualized, we will not claim that the device virtualization would work with our container solution. So, yeah. Specifically, also, this means for us Btrfs and not LVM, because we personally believe that, like, if you want to have a storage back and you want to be able to take snapshots, you want to be able to apply like changes and things like that. If you want to mark things read only, blah blah blah. Then all of that should be done with Btrfs, because we inherently believe it's a nicer design, and not LVM, for example, right? That's a choice, of course, that might be problematic, because Btrfs is not particularly stable yet. But we also believe, on the other end, that that Btrfs actually, like for the feature set that it has, and the feature set that we need for the specific use case of containers, it's actually without too much risk. Because, I mean, containers are something that usually live for only a very short time. Containers are something like where you start and stop them all the time. Usually the containers don't actually store the data locally. They usually contact some database, external database, or some cluster file system or whatever, which means that if you lose a container, right, because Btrfs didn't do the right thing, that's not too much of a problem, because, well, yeah, you don't lose any actual payload data. You will just lose the one container, and those you start and stop all the time anyway. However, actually, nspawn even works without Btrfs, except that a lot of the functionality that you have with Btrfs, like snapshotting, things like that, will then not be available. Yeah, what's also, I kind of already mentioned this, what's really, really important to us is that if we do containers, we really want to make sure that if an app runs inside of a container, it has the same APIs, the same behavior from the operating system available as it would if it would run on the host, right? It should be an implementation detail of how the admin runs something, if it's in a container or in the host, and the developer shouldn't really care, right? Specifically, this means, for example, /temp, how that is cleaned up, right? On the host, That's usually cleaned up automatically by time, so that if you drop in a couple of temporary files and you never touch them again, that after a couple of days they're gone again. But something like very superficial like that, we believe that it must be available on the host the same way as it is available in the container, right? Like we need to be able to clean that up in the container. So yeah, this is just one facet of it, right? Where it's not even an API really, it's just a general behavior that applications expect that /temp is cleaned up, and hence we need to provide the same thing inside of the container and on the host. What also is very important to us is that we actually really want to keep the doors open for alternatives, right? Specifically, this means much of the functionality that we implemented with nspawn specifically, you can actually plug any kind of container manager in, and you will get very, very similar behavior. How that exactly looks, we'll have a look in later. What's also really important to us is that we really wanted to avoid defining new standards where there already are standards. Specifically, this could, for example, mean that we don't define actually container form one, right? Like we don't do anything like Docker did, where you have these layers and you download the layers and stuff like that. We said, okay, containers are great, but we actually should just use whatever is already there. Specifically, like VM images, right? VM images, like raw disk images that contain a partition table in the file system. We thought, okay, this is actually fine as a container image format. Let's just make containers boot that. And that's what nspawn does, right? Like you can pass it either a directory that you want to boot, or you can pass it a disk image, like a GPT or MBR disk image, and it will boot that as if it was like basically KVM, except that it's not. It's actually just a container image. Then what's also important to mention is that for us, I mean, this is actually the history of nspawn, is for us, we test our system more regularly in containers actually than on bare metal. It's why we actually wrote nspawn in the first place, is because, I mean, we are init system developers, and as an init system developer, you have to test all the time if your init system actually boots, right? And if you would do that on physical hardware, you would have to wait a lot of time all the time, because you always have to go through the BIOS and wait until everything's booted up again. So back then, when we started writing this, we thought, okay, there must be a better way. And we played around with VMs. And then we realized that we probably actually want to use containers, and we played around with LXC, but we figured out that, oh my god, that's way too complex for us. We just want something that just works, that you can just point to a directory and we'll do the right thing. And given that containerization is actually not the most complex bit in the, not super complex, we just said, okay, let's just write our own little tool that implements namespacing, cgroup stuff, and actually sets that up. That's nspawn. nspawn, since then, like originally was this tool only for testing and building and things like that. Since then, it gained a lot of functionality, and is actually nowadays even useful for much more than just testing. It's not sufficient to just talk about what nspawn and the container stuff that we're doing is actually supposed to be. It also matters figuring out what it actually is not supposed to be, right? Where we draw the line between what should be in systemd and what shouldn't. One thing I would really like to make clear, for example, here is that cluster-wide orchestration is not the focus, right? This is something that Docker and Rocket and these kind of things are really strong on. But yeah, we don't want to focus on anything that like goes beyond the local machine, right? We want to be this container manager that just really runs container. And if you want something that actually orchestrates things across the network, then use something on top of it. But our tool will not be sufficient, right? This is a bit similar to how KVM relates to all the higher level managers like OpenStack or libvirt or whatever they're called, where basically, yeah, you use KVM as the lowest level component, but then you have this big software around that will actually distribute images across the network and things like that. So, yeah. And nspawn for us is like, we do the low level parts. How you push it on your cloud is completely up to you. Yeah, so while the cluster-wide orchestration stuff is not our focus and we don't want to have that in systemd, it still makes a lot of sense to build it on top. And Rocket is actually one of those examples where they did that, right? The Rocket Container Manager, what the thing that CoreOS came up with, is actually they use nspawn as the actual backend, and then they build all the orchestration stuff around all the downloading of the images and things like that. So, and we love that, because it's basically, yeah, we just do the low-level operating system integration, and they do all the complex stuff with actual web technology on top. So, so much about a little bit about the background of what we're doing and why we're doing it and how we're doing it and what's important to us and what's not important to us. Now let's actually have a look on the various components that the container support in systemd entails. This first thing I would like to talk about is machined. Machined is a small daemon that runs on systemd systems. It's usually not actually running, it's only started on demand. But what it's good for is that if there's a container running, like a container manager starts a container, then it can register that container with machined, and that basically enables a lot of integration into the rest of the operating system. There's one client command called machine control that you can actually use to then enumerate containers and introspect containers and things like that. Yeah, machine control is really just the client to machined. Again, what's really important to say is that machined is something that's completely open for other implementations. So any container VM manager can register its machines with it and gets the integration into the operating system that way. And a lot of the container managers actually have been patched that way. For example, libvirt LXC has, and LXC has, and things like that. And of course, Rocket gets it for free because our own tool does it too, which they built on. What does this actually specifically give you as integration? There are quite a few different things now. Like, for example, there's integration with system control, like all these commands that I've put here on the slide, which basically allow you, like system control -m is basically way how, I mean, I presume right now that you already have have come into contact with system control. System control is like this primary command that you interface, like you use to talk to systemd. It has a switch -m. And with -m, you can actually make a system control command not execute on the host, but on any local container that is registered with machined, right? So if you would normally write system control start foobar.service, you can just write system control -m valdo for container valdo start foobar.service, and then instead of the host, it will run in that container. There's system control -r, like lowercase r, which actually works, like it goes recursively into all the local containers, right? Normally, if you just type system control on the shell, you will see all your local services running. System control -r will show you the same list, but will also descend in all local containers and show you the services running in them, right? So it's a very efficient way to get a complete overview about what's running on the system, regardless if it's containerized or not. There's also system control list machines. System control list machines will actually just show you the local machines, and it will show you the health status of the systemd instances running inside them, right? The health status meaning if there is a service that failed and things like that, right? So it's a very useful command if you want to know in one command basically what's the health status of the host, what's the health status of all the individual containers, without actually looking at the individual services. Most of the other tools that we have in systemd, like login control, journal control, also got patched to have this -m switch. So login control login control is a tool basically which allows you to see who's logged in and what seats are there, what sessions are there, and so on. And login control -m just does that for any local container. Similar journal control is like the tool that allows you to look at the logs of your local system, and journal control -m then does that for any local container. Journal control -lowercase m is actually an even cooler command. What it does for you is it will collect the logs of all local containers, merge them into a single stream, and show it to you on the screen, right? So instead of looking individually at the logs of each journal, of each container, this one will actually give you a single unified stream, strictly ordered by time, that tells you what's going on in the system. It's a really, really useful command. But it doesn't actually just stop with systemd's own tools where the integration is. There's also integration with PS. You know, the PS command, the classic Unix PS command that shows you the processes that are running. Every container that's registered with machined will actually show up in PS, like there's a special column for it that will let you know which process belongs to which container. GNOME System Monitor has been patched the same way, right? Like you look at the list of processes, and GNOME System Manager will actually let you know to which container process belongs. Then there are some other commands in systemd itself which are really, really useful to use. Like, for example, systemd run is a really useful tool in general. Systemd run basically allows you to run arbitrary commands as a service, right? Normally you would just run systemd run, then specify a command line. This will fork off in the background a service. But systemd-run uppercase M is actually a way how you can run arbitrary commands in arbitrary containers that run locally. Then there's machine control login, that is, will just give you a login shell on any local container. Machine control stop kind of stops any container. It's kind of obvious, right? But it doesn't stop with all these commands. It also gives you a lot of other things, like, for example, automatic hostname resolution. There's this, I mentioned it already in the talk yesterday for those who attended it. NSS My Containers is a small NSS module that provides hostname resolution so that, any locally running container that has registered itself with machined can actually, the name of the container is resolvable automatically to the IP address. You don't actually have to do anything for that. All that's necessary is that the container has been registered with machined, and NSS My Containers will actually figure out the rest. It's actually a really cool feature. And NSS My Containers even does more now. For example, if you use username spacing, I'm not sure if you guys are aware of that concept. It basically allows you to run containers with a different set of users. And if you use NSS My Containers, this will also map the user IDs that you use for username spacing to useful names indicating to which containers actually belong. So, I probably shouldn't go into too much detail with that because it's very technical. Our APIs are also container aware if you register with machined. Like, for example, there's sdbus, which is our dbus API. Like dbus, I mentioned it yesterday, is this IPC system. And it has a call that allows you to connect to the local system bus, but it also has a call that allows you to connect to the system bus of any local running container. So, I guess what I want to say with all this is that on a lot of levels of the operating system, nowadays, like just by registering with machined, we expose and make the system aware of the container concept. Okay, so that was the first component, machine control and systemd machined. The second component is actually probably the most interesting one, which is systemd-nspawn itself. Systemd-nspawn is the actual mini container manager that we have. The concept there is that you just point it to a directory or to a disk image, and we'll just boot that up. That's really all that there is to it. It registers with machined, of course. And it's really, really minimal, but also really, really powerful. You pass a directory and we'll boot it. We suggest that you put your machines in, like your container images in valid machines, but you actually don't have to. You can put it anywhere. I mentioned this already. It supports GPT partition tables, also supports MBR partition tables, basically, so that you can point any raw disk to it and it will just boot it up. The exact same way how you can pass any raw disk to QEMU. The general concept we try to follow there is different from other container managers in regard that we think that a container should just be like a system service, right? Meaning that if you run 5 containers, they should just be 5 system services. So we call it container as a service in a way, because it's just if you run one process as a daemon or as a service, or if you run many and call that a container, should be kind of behaves the same way. Specifically, this means if you then type system control, you should see it in the list. All the local running services, all the running containers. It also means that resource management and things like that, and starting and stopping things, apply the same way to individual containers as also to the system services, right? Like, for example, if you want to say you want to bind your Apache service that's running on the host to CPU number 7, you can do that with a very simple system control command. But you can also, in the exact same way, bind the container that is running locally to CPU number 7. So, literally, like this container as a service thing is actually exposed in a way that you have systemd-nspawn add.service. To understand that, you need to have some experience with systemd, but it basically means that you have an instantiated service so that the that, yeah, you basically have one definition of how a service looks like, and then you can instantiate it as many times as you like. Oh yeah, I actually have this resource management example here. So you have system control set, oh, there's a typo, set property. You specify the service name and you write CPU shares equals 100. CPU shares equals 100 is something how you can alter how the Linux kernel will distribute CPU time between services. Normally it's a bit weight-based basically, so normally every service gets the default CPU shares value of 1024. And then everything that goes above that will get more CPU as everything else, and everything that goes below that will get less CPU. Because we set it to 100 here, it basically gets a tenth of the CPU that other services get. So this is actually really, really simple and really very much the same way as you would adjust the CPU time for any system service. Okay, so much about systemd-nspawn. Actually, I would like to demo this, and I hope this actually works, just to give you a feeling how this actually, oh, my battery is running empty. That's a bad idea. So let me continue talking while I actually plug in my power here. What I'm going to show you is actually how, is the power? What I'm going to show you is actually how simple the entire thing actually is. Oh, I should have power again. So I have this, can you actually see the command line that I typed in there? Let me increase the font. Can you see that? Is that okay? So what you see here is basically the most basic of the commands line that you can have, like the systemd, and actually the power doesn't work. That's weird. Oh, it's actually... Let's see. Oh, well, it works now. Perfect. So what you see here basically is the simplest command line you can type, systemd-nspawn -d. The D is for a directory. And then you specify a directory, and that's what it will boot up. So just to show that for a moment, or actually these mics work too, right? Actually put that here and talk to these mics instead. Okay, so what we have here is actually that in varlib machines, we have a couple of, or actually just one directory tree. If we actually look into that, what's actually in there, then we see that it's really just a directory tree how you would know it from any operating system, like it has var, user, temp, sys, srv, all these kind of things that you would expect from a directory tree. And then with the command that I had already typed here, we can simply boot that up. First we'll try it without the -b. What this does, it starts the container and gives you a prompt in it, right? So if we look into this, I mean, we see there's only like two processes running. One is the bash, like the shell that we started as PID1, and one is the command that I'm just typed, right? So this feels a bit like if you would take a Linux kernel and specify init equals -h on the command line, because it will just boot the system up but not actually start any init system, but instead just give you the shell. So this is already pretty cool. If you now look into the directory, like in the root directory, you'll see, okay, that's the same thing that we just saw in varlib machines. So far, so good. Let's make this more interesting. Now I just logged out with Control-D. Let's actually boot the thing up. Like if we do -b, then it basically will start the init system the same way as a Linux kernel would start an init system when it initializes the system. So if we type this, then what we'll see actually, it will just boot up and give you a shell. And that's really as simple as it is. You can take any Fedora image, any of the bigger distributions today, and just point them to a systemd-nspawn without any configuration. It will really just work. And then you can log in. And then you should not mistype your password. So, yeah, and there we are. And then if I look into that, I have my own little system. This time PID1 is systemd, and it all works the same way as it would on the host. So, we'll leave that container here running. Open a new shell. Now I actually need to increase the font again. If we now type the command machine control, we'll already see, okay, there it is, right? We called it Fedora tree. It will let us know it's a container and it's nspawn that registered it. If you use libvirt-lxc, if you use any of the other container managers that register with machined, you will see the same thing there. We can actually have a look at the container with this. So what I typed is basically machine control status. And what you see here is there's a lot of status information, like since when it's running, what's the leader process, what's the root directory, what's actually the operating system inside it. You will also see the unit name here, the unit name being the systemd service. And you see the process tree, what's actually running inside it. And this is nicely recursive, actually. So you'll also see at the end the logs from about the container. Currently not inside the container, but about the container. Let's play around a little bit with some other commands, like for example, journal control -m, which I mentioned earlier, right? We just specify journal oh, I need to do that as root, sorry. Journal control -m, you specify this, and then it will actually give you the logs of the container instead of the host, right? You see that in the fourth column there, the Fedora tree, and not my host, because my host is actually called Delta. But yeah, you can use any command. Like for example, system control on the host looks like this. Like you can browse here through the services on the host, but you can also do system control -m and run the same command inside of the container. And what we see actually here is that, oh, the power. What's going on here? Oh, no, it's good. No, it's good. And what we see here actually is that, yeah, Avahi failed because there can only be one Avahi instance running on the system at once due to multicasting, but that's another story. Yeah, you can even do something like systemd-run, just to give you an idea how that looks like. You can invoke, let's make this boring, we'll just invoke as a service sleep 5. If I run it like this, it runs on the host. But I can also do this. And then it runs in the container. And if we then, okay, 5 seconds probably too quick, let's turn it to 55. And then if we use this command again, right, we will see it, right, you see, I'm not sure if you see my mouse cursor here. Oh, you actually do. There we see this little service that was started, bin sleep 55. And that's actually really, really useful because you didn't even have to open a shell or anything. You can just start programs in any local container with this simple systemd-run thing. Yeah, what else can I show? Like machine control has quite a few commands these days. I don't really want to go too much into detail what they all do, but like list is the default one, shows you what is actually running. Status shows the details about one. Then there's login, right? Like just to show you how that feels. We just type machine control login Fedora tree. Oh shit. Yeah, there's a bug in there actually. So ignore that part. Yeah, this is actually something I really should fix. Yeah, there are a couple of other commands here. Like for example, you can make sure that the container started, boot and things like that. You can copy files from a container to the host and from the host to the container. You can make bind mount so that you can mount directories from the host into the container and things like that. Yeah. If you want to see, I hope I get the so just to give you an idea, like the integration into the rest of the operating system, I mentioned earlier that PS has support for using this machine information. Here you see one command line, ps-eo, and then we specify the columns that we want to see. So I now with PID machine args, comma args, it will show you basically the output where it has one column of the PID, one column of the machine things belong to, and one with the command line. And what you'll see here basically is that the commands that are run inside of the container actually have, yeah, the container name assigned then. So it's actually really cool. But let's return to my slides. Unless or anybody has questions so far, because actually I really like if you interrupt me so that we can turn this into a discussion the way you want this to go instead of me just talking. But if nobody has a question right now, I'll just continue with the slides. Okay, let's talk about the next thing. Systemd network D. Okay, now I should get this back here. Hello? Okay, it does. So the next thing I would like to talk about is systemd network D. I already talked about that yesterday, so this will be brief. Systemd network D actually comes with container support by default. Specifically meaning it will ship 2 configuration files. One that makes sure that when network D is run on the host, that every virtual Ethernet connection towards the container will automatically get a DHCP server run, and will get like an IP range picked. It will get IP mask rating set up, so that from perspective of the container, they can have like immediate access to the internet. There's the second configuration file that we ship is that when it only applies when network D runs inside of a container, and it basically makes sure that the other side works too, right? So that whenever it sees a virtual Ethernet tunnel to the host, it will just do a DHCP client and IP4L, and thus make sure that the other side works. Putting this together, if you run network D on the host and it's inside of the container, then you don't actually have to do anything. The networking will just work. I already talked about systemd resolve D in more detail yesterday as well. Systemd resolve D is, again, this thing that implements DNS resolution, like hostname resolution. It actually has support for a protocol called LLMNR. LLMNR is a linked local multicast name resolution. It's a protocol that Microsoft came up with. They use it for, I'm kind of repeating myself actually because I said very much the same things yesterday, so, but I'll repeat them anyway. So LLMNR allows you to, if you have an ad hoc network, right, like just 2 nodes connected via some Ethernet cable, so that it allows name resolution between those 2, right? In a setup where you don't have a DNS server and where nodes come and go dynamically at any time, right? Systemd resolve D with LLMNR works that way that, yeah, everything that is connected to your node that knows its own host name can talk to everything else, and everything else can talk to itself, all via the host names. The idea basically is that if you run systemd resolve D on the host and in each of your containers, the name resolution between them will just work as long as they share one direct virtual Ethernet link, right? Or actually you can even do that across networks, but that's completely up to you. If you have a virtual Ethernet network that spans a couple of hosts, then systemd resolve D will handle the hostname resolution as well automatically for you. So the idea is basically, yeah, to take benefit of systemd resolve D, you don't actually have to do anything. It will just work and just provide you with the hostname resolution, and you don't actually have to do anything for that. Yeah. So if you put this together and combine systemd network D and systemd resolve D, you should really have connectivity for the container out of the box, right? You have connectivity because you get the IP layer right, but you also get the hostname layer right, so that the container and the host see each other and you can contact them by their actual name. So much about resolve D and the container integration. Like, I mean, what's important to know is that we took some software that was developed, some protocol that was originally developed for ad hoc networks, for like embedded devices that talk to each other, and small consumer devices, and just said, okay, it's actually really nice functionality. We can also make use of this in the container world, so that the different nodes, container nodes that are in a virtual network can actually find each other. Let's talk about systemd D, which is another component of what we put together. Systemd D is actually, it's a very simple tool. It is, it just allows you to import container images onto your local system and run them. I cannot demo this right now because I don't have internet here, but it's basically you just, it's also integrated with machine control. Machine control, like the machine CTL tool, is also a client to systemd D, not just to systemd machine D. And you could just pass it in URL, and that URL can point to either a raw disk image or to a tarball, and we'll download that and put it in valid machines. It does it the right way, so it will also do decompress things, it will also do GPG verification, and simple things like that. And it also can do QCOW2, like the QEMU images. And then, yeah, we'll just place them there, and you can boot them up with systemd-nspawn. So yeah, it can do tar and raw, and it actually also has import-only support for Docker images. If you want to play around with that, this is like how a command line looks like. You just type machine control pull raw. We turn off verification in this case because the Fedora cloud images don't provide signatures right now that could be used for our stuff. And then you just specify the raw disk image, and this will download the image, and then you can just spawn it with systemd-nspawn-m. So the key takeaway here is that we decided not to come up with any container format, but instead just wanted to make sure that the cloud images that the various distributions provide anyway just work in containers without modification, right? And then we thought, okay, then let's write a minimal tool like machine control pull raw, where you just specify the URL, and it does everything right, and then you can just start it. The machine control tool actually works better, ironically, on Ubuntu images than on Fedora images, even though I'm, of course, a Red Hat guy. The simple reason is that this signature stuff is set up properly for Ubuntu, but Fedora has not made the change yet so that we cannot automatically do the GPG verification of the images we download. So that's why we have the -- verify equals no. If you have an Ubuntu image, you don't have to do the -- verify equals no. Okay, so much about the different component that we have. At this point, let's do more questions. I mean, I have a lot more slides, but I'd really much rather turn this into a discussion. But nobody has any questions. There were people yesterday who had container questions.
Hey, I'm back. I wanted to ask you about the plans of the systemd as a project to interact with the open container project recently announcing, because I see a lot of overlap with what you're doing about image verification and standards and formats. Could you comment on that, please?
So I'm not involved in the open container stuff. I have seen the specification, how it looks right now. I can't say I'm not particularly happy with what they came up with so far. You know, that was not a good idea. The way I see it is basically I just want to do the basic building blocks of things. And defining container format is not necessarily what I think is a basic building block, right? Like, that's already higher level stuff. The Rocket people did that, for example, with Rocket. Rocket has its own container format. And I kind of hope that the Rocket people will make sure that the specification looks good in the end. But, yeah, right now I'm not really involved, and I'm not sure I want to be involved. There are lots of stuff in the specification parts that I've seen so far that I really did not like. Like, for example, they expose way too much information about the Linux kernel in the image format that they really shouldn't be exposing. Yeah, I don't know. I think it's a good idea if they become friendly, like, because there was this conflict between Docker and Rocket, and if they can come up with one solution, that would be, of course, be great. I really hope it's going to be a good one. If I look at like what Docker has done there with verification and things like that, I think it's close to being insane what they're doing. But I don't know, like, for us, I want it much simpler and much more low level, and hence that what they do is really out of focus for us. I mean, to make this very clear, I don't actually want to be in competition with Docker or Rocket or anything like that. I just want to be the guy who does the low level stuff, and other people then build something on top of that. And that's Rocket, for example, for us, and that's the way I like it. And if they can deal with open containers and can add open container support to Rocket, that would be perfect, because that's how I would like to see it. Hope that makes sense. Anybody else has questions? There's a question.
Hi. I would like to know if there are any plans about integrating for desktop stuff. For example, using containers for dumb terminals, like sharing hardware.
So, like, what do you mean? You mean the device virtualization, like how you can actually have devices from the host available in the container? Is that what you were asking?
About running, how can I explain it? For every client that connects on the server, I boot up a new container for serving a desktop for the user, like you can do with Windows Server, Windows Terminal.
I mean, you can do that, absolutely. So you want virtual desktop sessions, basically.
Yeah, that's it.
I mean, you can do that. I mean, the containers, like how we implemented them in nspawn, are really just normal systems, right? So if you can do that automatically, like spawn up a new system and then go into it via Spice or X or whatever you want to use for networking. But it's really just, it is the same as if you would start off up a new system somewhere else on this world, because like it's connected via networking, right? So I don't know of any ready solution for this thing, but I'm pretty sure you can easily build that without too much work. You can just start up a container, stop it after the user logged out. Yeah. Is there any further question at this time? There's one.
It's probably regarding a map implementation in the kernel. If I want to share shared libraries between a container and the host system, is it possible, or the map implementation does not share the same mappings for files?
I mean, if you want to share shared libraries,
shared code.
It kind of defeats the point of containers, right? Because I mean, if you share them, like what you want to share between host and container, or do you just want to have multiple containers using the same shared library?
Well, I could use both. I could use like a share between containers and between the host and containers.
I mean, what you can do, like what we would like to go towards with systemd, it's actually one of the other slides that I have, is that we can go to a scheme where you have one container tree, and then you instantiate multiple instances of this container tree, right? So that you run 100 container instances, and you use the exact same /user for every single one of them, so that the libraries that are inside of them are shared in memory. Like they will only exist once, but you have a lot of containers running off them. So you can do that kind of stuff. But I mean, if your question is really regarding packaging stuff, right? Like how you want to be able to use containers without actually using containers, I think it kind of would miss the point of containers, right? Like if you just run with the same set of libraries as on the host. Because I mean, the good thing about containers are really that you disconnect the versioning of the libraries and the programs in the container from the versioning libraries on the host, right? Yeah. So, but if you don't want that, then you probably don't want containers, if you follow what I mean.
Right. Cheers.
How much time do I have? I probably have a minute or something more. Anybody has a question? No questions. So let's see if I actually have a minute. Time is it? Okay, I got 3 minutes. So if nobody has a question, then I'll do another slide. Actually about the stateless system stuff. So I already mentioned this in the answer earlier here. What we want to really go towards, and I actually mentioned that yesterday, I think, too.
Hi, Lennart. I'm sorry to interrupt. Just a question here.
Where? Okay, there.
When you boot the container, you start systemd inside the container, and how does it communicate with the systemd that's running on the host?
No, it does not. Like unless, I mean, system control, like the client side, that can communicate with any systemd. But the systemd on the host and in the container do not communicate. Like the system, like nspawn will set up the environment in a way that systemd in the container can work well. But it will, they don't communicate. It will just set up the environment, invoke systemd inside of container, and then it's the container does whatever it wants.
And is the systemd running inside the container aware that it's running on the container? Is that something that is important?
No, so basically, we just, I mean, the systemd inside of the container will run in a slightly different environment than it would run on the host, right? For example, if you run a systemd on a host, it needs to do device management and these kinds of things. But in containers, devices are generally not available, so all the device management will be disabled. right? So systemd inside of the containers is aware that it runs in container, but usually we actually don't want to hard code it in that way. What we instead do is we check specifically for features, right? So instead of saying, okay, we behave differently in a container, what we actually do is like we behave differently in a system where device management is not available. So that in theory you could actually build a VM or something which also lacks device management, and systemd would do the right thing. But yeah, the systemd inside of the container knows that it runs in a container, and it will behave slightly different. But again, we try to not have code in systemd that explicitly checks these things, but sometimes we actually have to have that. I guess those were my 3 minutes, unless somebody here has a final question.
Eu gostaria de saber se tem como eu rodar processo num container.
I didn't understand that, but I have this thing here. Do I have to turn this on?
Posso falar? Então. Acho que é um off. Eu gostaria de saber se tem como eu rodar processo em determinado container e por algum motivo eu queira que ele esteja rodando com outro processo num outro container. Eu consigo migrar o processo de um container para o outro? Não.
That is a very good question. There are projects like CREU, like checkpoint restore in user space, that implement something like that you can actually serialize a container or just a single process and deserialize it somewhere else. I must personally say I don't really believe too much in that concept because it is it's a game that sometimes works but not always works, right? Like it's a weird promise to make. Like if we write software, then we really should write software in a way that we know that it will work whatever the setup is of the user in the end, right? But checkpoint restore is something that, yeah, it works in many ways, in many cases, but because some of the functionality of the Linux kernel cannot be serialized like that, it doesn't work always, right? So I personally don't believe too much in that concept. Also, from the other end, containers are something that are very different from a normal host, right? Containers are something that they are very transient, very short-lived normally, and you usually run many instances of them. Hence, I think it's much less interesting being able to save and restore things and migrate things, because, well, if you want to do migration, just start a couple of new containers on the destination host and solve it that way. So, I don't know. I know that many people care about this, and there are implementations to do this, and LXC and things like that to support that. But I'm not convinced that this is a generally useful thing, and I'm not convinced that we want to have that in nspawn. I know that that's disappointing in many ways. Anyway, I think that was really my time. I hope that the answer was useful. If you have any further questions, ask me in the hallway. I have more slides here. I did not intend to actually cover them all, which is completely okay. But I think I put them online somewhere. And yeah, if you ask me later, I can tell you where to have a look on the slides. Anyway, so thank you very much for your time. I hope this was useful.